Welcome back to ECE 320A. We're in Unit 10, which is the Bode plot unit, and that is covered in Appendix E at the following pages. And homework 10 you need to complete at the end of this unit. And after this unit, you will also be quizzed via exam number 4. As I've said before, we're breaking down these Bode plot sketching strategies into fundamental pieces. We've already talked about how to factor, how to identify the different factors, constants, poles or zeros at the origin, linear factors, poles or zeros, and quadratic factors. In this video, what we want to do is focus on sketching the constant factor in our transfer function. Don't lose sight of what we're trying to do. We're simply developing strategies for quickly drawing straight line approximations to give us our frequency response behavior of a transfer function. And that frequency response will be in the form of two different plots. A magnitude plot, which the magnitude is expressed in decibels. That allows us to add up the different pieces that we learn how to sketch, and the phase plot, which is now the angle as a function of frequency. And again, we'll just figure out how to sketch the angle behavior of each of these different factors. And then at the end, the angles just add algebraically. If we have zeros, those are plus signs. If we have poles, we'll just subtract those angles in essence. Again, we're developing these strategies for a minimum phase transfer function, which means when it's minimum phase, that just means that all of the poles and zeros are located in the left half of the complex plane. Again, our strategy is to break this process down into sketching the individual terms. And then at the very end, after we've put all of these flavors together on one plot, then we combine those into a sum of the magnitudes as you go from low frequency to high frequency, and the sum of all of those angle pieces from low frequency to high frequency. In this particular video, we are going to focus on the constant flavor. I'm calling them flavors just so that you have something to think about, or maybe you're hungry and now you want to talk about Bode plots. So now, over your meal, think about sketching the constant in this particular piece or strategy for sketching Bode plots. In our particular example, we had factored out the poles and zero locations, the constant terms in our pole zero form, and converted that transfer function into time constant form, and that left us with a k equaling 0.02, or 2 times 10 to the minus 12. We now want to draw that as a function of frequency. And hopefully you can see that there's no omega anywhere in that k expression. So that means if we can just find that magnitude in dB, then it's going to be that fixed magnitude for all frequencies omega. And you're going, well, what's the angle of k? Well, this is now a positive number. So the angle, if you think about this in terms of where is this point located, you could locate that in a complex plane and say, oh, that's on the horizontal real line, and the angle of that horizontal real line location is 0 degrees. If k was negative, so now I'm talking maybe in thin air, but let's now say that we now had this real value out here at 2000 or 0.02, then the angle that I have to look from here to there, I don't have to move my neck anywhere. I just keep looking straight ahead. So this angle is actually 0 degrees. Contrast that if K was now equal to minus, let's say, 6, then I might be over here, and now the angle that I have to turn my neck through, I can go either clockwise or counterclockwise. Let's go ahead and look clockwise so that now we are looking at moving through an angle measured with respect to the positive horizontal real line. Now we move a full 180 degrees. So the angle associated with a negative number would actually be minus 180 degrees. For our case, for this particular transfer function, we've identified our constant to be 0.02. That has a positive sign associated with it, which means that we are over here or with an angle of 0 degrees, and that 0 degrees doesn't have an omega associated with it, so it's 0 degrees for all frequencies. And that particular phase curve, due to this constant, is very easy to sketch. It's just 0 for all frequencies. Let's look at the magnitude. So now we're looking at 20 times the log of the magnitude of the constant. The magnitude of a positive 0.02 is 0.02. And if we write that as 2 times 10 to the minus 2, we can now use the property of the logarithm to say the product of two values is the sum of logs, or the log of a product is the sum of the logs of those two terms. So we now have log of 2 plus log of 10 to the minus 2, all scaled by 20. We can't lose track of that. And log of 10 to the minus 2, that exponent jumps out in front. So now we have minus 2 log of 10 base 10. Well, the log of 10 is 1. So now we've reduced this 10 to the minus 2. Its base 10 log is now just minus 2. And we have to now remember or compute what is the log of 2. And hopefully you'll start to become a little bit more comfortable with some of these logarithms of in a certain real values, 2, 4, 8, all of those are scaled by 2, and so now we have 0.3, 0.6, and 0.9 for the log of 2, the log of 4, and the log of 8, and we only really have to worry about a few more of those values to sort of be able to quickly find those locations along the log of omega axis. But in this particular case, let's go ahead and do the math associated with this. We could now say, oh, we have 20 times 0.3, or that's now 30% of 20, that's now 6, and we have 20 times minus 2, which is now minus 40. So in fact, we now have, for a magnitude for this transfer function, it was 0.02. If it's now less than 1, we're going to have a negative dB, and in fact it's now minus 34 dB. And you might sort of, to get some insight into what's happening, you could say, well, where am I going to fall relative to minus 34 dB, or what am I sort of in between? You can think about some bounds. If we looked at 20 times the log of 0.1, the log of 0.1 is minus 1, so that's minus 20 dB, and 20 times the log of 0.01, we're between those, we're at 0.02, but this log of 0.01 is minus 2, so this is now minus 40 dB. And now we've checked our work. Okay, minus 34 dB sounds about right. So now we want to sketch that as a function of frequency. We want to draw minus 34 dB, and you can see in that number It's just a number. There's no omega anywhere in that expression. So now we simply draw that minus 34. So if I can now be somewhat, this is now our minus 34 dB, and that's now the magnitude of our constant in dB for all frequencies. That particular constant produces that contribution to our Bode plot for this particular transfer function. And that wasn't very hard. The phase is even easier because now, as we said before, since this is now k equaling 0.02, the angle of k is now the angle of 0.02, and if we wrote that in polar form, that's now the 0.02 at an angle of 0 degrees, so this is now 0 degrees for all omega. And now, if you wanted to sketch the contribution that that gain provides to the phase curve, it's just contributing 0 degrees for all frequencies from small to large. And I'm not saying from 0 because we're on a logarithmic axis. Now we just keep going, 10 to the minus 2, 10 to the minus 3, back to the left. We're never going to reach DC or the origin, and we're never going to run out on the right of higher frequencies. We just keep going because we have a log of omega axis. If k, as I had said before, was something like minus 6, then if we looked at the angle of k, which is now the angle of 6 at minus 180 degrees, this is now minus 180 degrees, and we would have that for its phase contribution as a function of frequency. I hope that now gives you a feel for how to sketch magnitude and phase as a function of frequency for different gains. Here we had a gain less than 1. If our gain k was, let's say, 10, then we would have 20 log of 10. Log of 10 is 1, so we would have 20 dB. And now we would have something that's up here at 20 dB for all frequencies. I'm going to go ahead and remove that because people will wonder what that's for if they now see this video. But that's now where you would sketch this magnitudes Bode plot contribution on the Bode plot axis or on the log of omega frequency line.